So in this video, we're going to look at percent error calculations. So most often we'll be calculating percent error during the lab portion of this course, but we'll also see a few problems during the lecture. So we're going to start by looking at a word problem asking us to calculate percent error. So in this word problem, it's telling us that a student measured the density of water to be 0.915 grams per mil. So those are the units on density. The actual density is 1.00 grams per mil. It then asks us to calculate the percent error. So in order to calculate percent error, you need to use the percent error equation. So let's look at some features of this equation. In the top, we are going to take the measured amount and subtract the true amount from it. Notice these bars on either side of that subtraction. Those are called absolute value. So if you happen to get a negative when you do this subtraction, a negative number, those absolute value bars are telling you to change that number to a positive. The magnitude of that number will not change at all, just the sign of the number is going to change. These can also be construed as parentheses, meaning do the subtraction first, and then once you get the subtraction part finished, you're going to divide by the true value. Of course, don't forget to multiply by 100. This is what gets it into a percent. When we're doing these calculations, we're not going to have actual units. So what I mean by that, in this case, we're taking grams per mil are the units that are going to be on the top, and grams per mil are the units that are also going to be on the bottom. So these units are going to cancel each other out since we're dividing, and so all we'll have is a percent sign at the end of our answer. All right, so now let's try to apply this. So we're going to look at the word problem, and our goal here is to figure out, okay, which one is the measured, which one is the true? That's the hardest part, is figuring out which is which. So for the measured, in this particular question, it specifically says the word measured. The student measured. Another word that might be used in a different word problem could be experimental. So whatever the student, the scientist came up with, that's going to be your measured or your experimental, and that's going to go in this spot here. So the 0.915 is our measured. The actual, so that's a key word here, the actual density of water is 1. So actual, that's just another word for true. This word here. So if you see the word true, actual, theoretical, so that means this is the values from the table. This is the proven value. That's the true value, the actual value. Okay, so let me add another word here. Proven might be another word used. So that's going to go in these two spots, and that's 1.00. So let's plug it in and see what we get. So the measured is 0.915. So I'm going to put that guy here. The true is 1.00. So it's going to go here and here. So 1.00, 1.00. Now I'm going to calculate this out. So I'm going to do the subtraction first. So 0.915 minus 1. Now I get a negative number when I do that, but because there's absolute value signs, I'm going just to change that negative to a positive. Since I'm doing a subtraction, I'm going to look at my decimal places. So this number goes out 3 decimal places. This number goes out 2 decimal places. So I'm going to want, I'm going to write it down here since I don't have any room off to the side. I'm going to want 2 decimal places in the numerator for that subtraction answer. So when I subtract those, I get negative 0.085. Well, because of the absolute value, I do not want the negative, so I'm just going to erase it. That's what the absolute value means. Just take the negative away. Now, I also said I want 2 decimal places. So 1 decimal place, 2 decimal place. Look at the number next to it. that 8 is going to become a 9. So on the top, in the numerator, I'm going to want 0.09. So that's what my top says. Now on the bottom, I'm just dividing it by 1. And I'm not going to forget to multiply by 100 to get it in a percent. So I am taking in the numerator from that subtraction, after doing the absolute value and counting out my sig figs based off the fact this is subtraction and I'm looking at decimal places, I get 0.09 in the top. I'm going to divide that by 1, which of course is just 0.09. Then I'm going to multiply it by 100 to get it in a percent. And that is going to give me 9%. Is that the correct number of sig figs? Okay, well, let's look. So we're looking at this problem separately. We have 1 sig fig, just the 9, in the numerator. We have 1, 2, 3 sig figs in the denominator. We want to pick the smallest of the two, and that's a 1. So yes, we do just want 1 sig fig in our answer. So 9% would be the correct answer. Let's look at one more problem. So another percent error calculation. In this case, we have a student dropping a tennis ball from 60 centimeters. So this is something we actually do in lab 1 in the physical science lab. It took the ball 0.61 seconds to reach the ground. Given that the rate of gravity is 9.8 meters per second squared, it should take the ball only 0.56 seconds to reach the ground. What is the percent error? Okay, so this one might be a little bit trickier because of the words being used. So we have percent error, we have actual minus true divided by true times 100. Absolute value signs. So we need to know what's the actual, what's the true. Well, there's tons of numbers in here, okay? So we need to figure out what numbers are important because we only need 2 of the numbers. So how do we figure out what we're comparing? Well, let's see. Using the units is probably going to be your best bet. So what I mean by that is we have centimeters, we have seconds, we have meters per second squared, and we have seconds again. So I'm going to go ahead and guess that these 2 numbers are going to be the 2 numbers that I'm going to plug in here because they have the same units, and we can only compare 2 numbers if they have the same units. So now I just need to figure out which one of these is my actual and which one of these is my true. Just trying to confuse you here. Which one of these is my experimental, sorry, and which one of these is my true. So looking at it, you have a student dropping a tennis ball. So whatever the student's doing, whatever the scientist is doing, that's your experimental. That is your measured, okay? So the student dropped it in this experiment and they measured the ball to take 0.61 seconds to hit the ground. So this is going to be your measured, your experimental, which means the same thing. That's going to go right here. So let me write it down below. So 0.61 minus, that by default is going to mean that the 0.56 is the true value, that theoretical value. So some clues that might help you with that as well is it said, given that the rate of gravity is 9.8 meters per second squared, it should take the ball. So this is the true, that's how long it should take, the actual. All right, so we're putting that here, and it's also going in the denominator. Remember to do that subtraction first. If you get a negative number, just change it to a positive. That's what the absolute value signs are for. So I get, carrying this over, 0.05 on the top, because I went up 2 decimal places, 1 2 decimal places, 1 2 decimal places. So I stuck with sig figs there. And then I'm going to divide that by 0.56 times by 100. So notice my answer is only going to have one significant figure in it. So when I take 0.05 and I divide that by 0.56 and then multiply by 100, I get 8.928. So 8.92. But I said I just wanted one sig fig. So stop here, look at the number next to it. Is that going to stay at 8 or move up? It's going to move up to a 9. So we get 9% once again. That was complete coincidence that we had a 9% error for both of those problems. So that's it for percent error.